I'd like you to imagine objects A and B, and what we're going to look at is a collision between these two objects. Now, when they collide, we've got object A will experience a force A due to the action of object B. And likewise, object B, because it's being hit by object A, is going to experience a force in this direction, which we're going to call force B. Now, by Newton's third law, the size of force A on object B is equal to the size of force B on object A. And what we can say then is that FA is equal to FB. The other thing is that this force is going to act for a certain amount of time t. Now, it's kind of obvious really, but the time that the blue one is in contact with the red is the same as the time that the red is in contact with the blue. And therefore, the collision time is going to be exactly the same for both of them. And because they have the same collision time, that means FA times the change in time is going to be equal to FB multiplied by the time for that collision. So I've just put in a time into both of this. And what we have now are some impulses. Okay, so this is the impulse, and this is an impulse as well. And the impulse is equal to the force multiplied by the time for which it acts. And what that does is it changes the momentum. So the change in momentum is going to be equal to the force multiplied by the time for which it acts. And because we've got the same size force and the same time for the collision, that means the change in momentum of object A is going to be equal to the change in momentum of object B. Now, so far we've looked at the magnitude of that change in momentum. But the important thing to note is really that because these two things have opposite velocities when they move in, that means they're going to have an opposite change in momentum. One's going to increase and one's going to decrease. And really, we can say that then that the change in momentum of A is going to be negative the value of the change in momentum of this. And that means that if we add these two momentums together, the total change in momentum is going to be 0. So provided there are no external forces acting, if we have two objects that collide, the net change in momentum is going to be equal to 0. So the principle of conservation of linear momentum really states that the total linear momentum of a system remains constant in collisions, so that's things moving together, or explosions when they move apart, provided no external forces are applied. And as an example of this, you often get questions about weapons and how bullets are fired from guns. So we'll have a look at that in a bit more detail. Now the actual projectile which is launched at the front of a gun is actually quite small, and this is the size of a bullet from and this one's actually a 5.56 rifle, and it comes in a round a bit like this. So you've got the bullet and you've got the casing which has the explosive or the propellant inside of it. But what I'd like to do is really just consider what happens to the bullet after it leaves the pistol and how quickly the pistol recoils. Now we do need a bit of data to do this. So first of all, here's some data. The mass of one of these pellets, or one of these bullets, sorry, is normally about 7.5 grams, okay? And they might come out with a velocity of maybe, I don't know, 380 meters per second, okay? This weapon here, it's got a mass of about 0.430 of a kilogram. And with this information here, we can work out how quickly this rifle recoils, or how quickly the pistol recoils when it's fired. Now, before anything happens, and the bullet's actually inside the weapon, this thing is stationary, and therefore the initial momentum is equal to 0 because nothing is moving. Now, we know from the conservation of momentum that the momentum after the explosion is going to be the same as it was at the start. So we can also say then that the P final, or the final momentum, is also equal to 0. But what is this final momentum made up of? Well, first of all, you've got one thing which is moving to the left, and you've got something else which is moving to the right. So we can say that that final momentum, P, is equal to the mass of the bullet multiplied by the velocity of the bullet, added to the mass of the gun multiplied by the velocity of the gun. Okay, so we can then start to put some numbers in. Now we know that the final momentum, like the initial momentum, was 0. This is equal to the mass of the bullet, which in this case is 7.5 times 10 to the minus 3 kilograms, multiplied by 380 meters per second. So this is all the data for the bullet that we have over here. In terms of the gun itself, well, it's going to have a mass of 0.430, and we don't know how fast it's moving off at. And I'm just going to call this V. Okay. Now, if we've got the bullet moving off to the left-hand side, let's take in this direction. The direction to the left is a positive direction, which means any direction to the right is going to be negative. So what we have now is all the data we need, and we can then start to compute this and actually work out the velocity of how quickly that gun moves back. So I've put the data in, I've rearranged it, and I found that this thing actually moves off initially at 6.62 meters per second. Now in that last example, we just considered a pistol acting on its own, and it had a recoil velocity of over 6 meters per second. The reality is, when you actually have a pistol like this, it's also attached to a person, and they've got their arm, the mass of their arm, and the mass of their body to consider as well. So their total mass is going to be, or the total mass of the weapon is going to be greater than just the mass of the individual firearm itself. So the greater the mass, the lower the recoil velocity. But still, when you have something which is very small heading out one way really fast, it's got the same momentum as a larger thing which is moving away quite slowly.